Dear students, in the last class, we have introduced autoregressive and distributed lag models. Why dynamic nature of relationship is important in economics. How to make a relationship dynamic by introducing lagged values of the independent variable in the consumption income example, and we have specified a number of instances in which there is lag of adjustment between y and x. Now let us specify or elaborate these points a little more to give more insights into the nature of dynamic relationship between variables. As we know, in cross-section data, as data is collected by what is known as random sampling, it is assumed that different sample units are independent. For example, if you study a relationship between consumption and income, if there is any disturbance in the consumption income relationship in a particular family, it will not affect the consumption income relationship in another family. So the data points will be uncorrelated. But in time series data, as we are collecting observations over a number of time periods from the same economic unit, successive values of the data points, the sample values will be interrelated. For example, in the consumption income relationship, the values of consumption and income in any time period will be affected by its values in the previous time periods. So, in the time series analysis, successive values of x and y will be interrelated. So unlike cross-section data, there is a problem of modeling, incorporating and modeling this, what is known as autocorrelation, a topic which we have extensively discussed in the previous classes. Autocorrelation, its causes, consequences, remedies and like. This is one issue, one aspect of time series which make time series data different from cross-section data. The second point is, unlike the cross-section data, as we have discussed in the last class, time series data portray the existence of dynamic relationship. Unlike cross-section data, there is dynamic relationship between variables in time series data. A dynamic relationship is one in which a change in one variable will have effect on another variable in the current time period and many future time periods. A dynamic relationship is one in which a change in one variable at today, at now, will have its impact on that same variable and also other variables in many future time periods. That is, if there is a change in the value of one variable, its effect will be felt on that variable and also many other variables today and also in future time periods. As an example to this, suppose that there is an increase in the income of the consumers today. If the income increases, it happens that consumers have more disposable income. And when consumers have more disposable income, they will increase their expenditure on goods and services. And the increased demand for goods and services increases the profit of the entrepreneurs, and the increase in the profits on the entrepreneurs increases the demand for inputs, and it increases the income of suppliers of inputs and the like. So the effect of a given cause is distributed over many time periods. The effect of a given cause is distributed over many time periods. An increase in income will have impact today and also in many future time periods. And given that there is dynamics in the nature of relationship between y and x, between dependent and independent variables, the question is how to model such a dynamic relationship. How to model such a dynamic relationship. We specify three ways in which the dynamic relationship can be modeled. One is we specify yt as a function of xt, xt minus 1, xt minus 2, like this. We specify yt as a function of xt, xt minus 1, xt minus 2, etc. As an example, we can say that the current rate of inflation, yt, depends, suppose that yt is inflation, then the current rate of inflation depends not only on current interest rates, but also on past values of interest rates. Past values of interest rates. Current rate of inflation depends on current interest rates and also past values of interest rates. This can be stated differently. If there is a change in the interest rate today, its impact will be felt on inflation in the current period and also many future time periods. If there is a change in the interest rate today, its effect will be felt on the inflation rate today and also many future time periods. Both statements are correct. One statement is inflation depends on current and past values of interest rates. Second, a change in the interest rate today will cause change in the inflation rate today and also many future time periods. For example, and we can say an economic action at t, time period t will have the effects at t at t plus 1, effect at t plus 1, then effect at t plus 2, etc., etc. And as we have stated in the last class, as there is the existence of a lagged effect, such models are known as distributed lag models. Such models are known as distributed lag models. the effect of a given cause is distributed over many time periods. The effect of an increase in interest rates will be distributed over many future time periods on the rate of inflation. Or today's inflation depends on past values of interest rates. So, as the effect of a given cause is distributed over different time periods, it is known as distributed lag models. If there is an increase in the income, then its impact on consumption will be felt in the present year, next year, after 2 years, 3 years, etc. So the cause is an increase in income. Its effect is felt over many time periods. So such models are known as distributed log models, and distributed log models are dynamic models because the effect of a change in one variable will have an effect on the same variable and also other variables today and many future time periods. So this is one way in which we specify dynamic nature of relationships. The second way of specifying the dynamic nature of relationship is we specify yt as a function of xt and also yt minus 1. We specify yt as a function of xt and yt minus 1. Such models are known as autoregressive models. And in this case, if this is the model, we say that inflation at a time period t depends not only on interest rate at t, but also the value of the rate of interest in a previous time period. Today's inflation rate depends on inflation rate in the past period. So, as there is a positive relationship between inflation rates, if inflation rate in the last period is very high, it will be high in the present period also. So, these types of models are also dynamic models, and such models are known as autoregressive models. And remember this, actually there is no difference between these two types of models. The reason is, if we specify a distributed lag model like this, by giving some adjustment process, as we will see later, it is possible to convert such a distributed lag model into autoregressive models, where yt depends on xt, yt minus 1. A third model which we consider is the autoregressive distributed lag models, where yt is a function of yt minus 1, xt, xt minus 1, xt minus 2, etc. Such models are known as ARDL models, autoregressive distributed lag models. Such models are extensively used in time series analysis, and we will see such models in detail later. So these are the three ways in which we model dynamic relationships. One is distributed lag models, second is autoregressive models, third is autoregressive distributed lag models. To obtain further insights about the nature of dynamic relationship, consider a distributed lag model like this. Consider a distributed lag model. Suppose that yt is equal to alpha plus beta xt plus beta 0 xt plus beta 1 xt minus 1 plus etc. beta k xt minus k plus ut. Consider a distributed lag model. It is an example of a finite distributed lag model as the lag length k is xt minus k. If k is 5, xt minus 5, k is 6, xt minus 6, like that. It is an example of a finite distributed lag model. Now the model says that the value of y is related to xt and lagged values of xt. The relationship is also linear. If you have data on y and x, taking k lags, you can estimate such a distributed lag model. And this model says that if xt will be affected by yt over a period of t minus k. Beyond that, there is no effect. If there is a change in x, y changes from t is equal to 1 to k. Beyond that, there is no effect. Such models can be used for forecasting purposes. It's a topic which we will discuss later. Can also be used for policy analysis. Used for policy analysis by the government agencies, by private firms and other institutions. Now, to give an interpretation to the coefficients, betas, let us see how we interpret the coefficients betas in this distributed lag models. Yt depends on xt, xt minus 1, etc., xt minus k. And in this specification, the coefficients betas give a change in expected yt when xt minus s changes by 1 unit. Beta s is equal to 1 to k. Beta s changes gives change in expected yt. Change in expected yt when xt minus s changes by 1 unit, but changes by 1 unit. And alternatively, as I discussed earlier, if we look forward instead of backwards, beta s gives the change in expected yt plus s. Expected change in yt plus s when xt changes by 1 unit. Xt changes by 1 unit but held constant in other periods. That is, dou expected yt by dou xt minus s is equal to dou expected yt plus s by dou xt is equal to beta s. We can interpret beta s either as a change in y due to change in xt minus s. That is, xt minus 1, xt minus 2, xt minus 3, etc. Or a change in yt plus s, yt plus 1, yt plus 2, yt plus 3, etc. for a unit change in x. So if we interpret it like this, if it is inflation and if it is interest rate, then the interpretation is, if interest rate changes by 1 unit, inflation changes in the same period, 1 period after, etc., s periods. Or we can say, if there is a change in the interest rate at t, its impact on inflation will be felt at t plus 1, t plus 2, t plus 3, and the like. Both interpretations are same. It will give us beta s. Now, in this equation, we can say that, suppose that x and y constant for k periods and that xt is increased by 1 unit, then it is retreated to its old level. Xt and yt remain constant for k periods, then xt increases by 1 unit. Then it comes back to the original level. Then the immediate effect on yt is given as beta 0. Dou expected yt by dou expected xt, beta 0. Dou expected yt by dou expected xt. Then 1 period later, it becomes beta 1. Dou expected yt by dou, or we can say 1 period later means expected yt plus 1 dou xt. That is beta 1. After 2 periods, it becomes beta 2. After k periods, it becomes beta k. After that, it will come back to the original level. Now, the effect of a given change in x in this example is distributed over a period of k. Period of k. Now, it is as the lag length is specified, it is an example of a finite distributed lag model. And the coefficients are the weights in this scheme. And beta 0 is known as we have discussed in the last class, the impact multiplier. Dou expected yt by dou xt is impact multiplier. Beta 1, beta 2, etc. beta k. That is dou expected yt plus 1, dou xt, yt plus 2, dou xt, etc. are known as interim multipliers. And if you add together all these, beta 0 plus beta 1 plus etc. beta k, you will get what is known as total multiplier. Total multiplier. So remember this, in the distributed lag models, we model the dynamic relationship between variables. And remember this in economics, as we have discussed in the last class, changes are not instantaneous. There is always a lag between the change in the value of one variable and its impact on other variables. Such a lapse of time is known as lag. And the question is, if there is a lag in the adjustment process, how to model this lag, or how to model the relationship between variables taking into lag in consideration. And there are 3 ways in which we can consider this lag. One is the distributed lag models, the second is the autoregressive models, the third is a combination of autoregressive and distributed lag models. And in the distributed lag models, these coefficients are constants in the nature of dynamic relationships. That is, the effect on y for a unit change in x at a time period during the same time period, if we are using the using yearly data in the same year, after 1 year, after 2 years, etc. If there is a change in interest rate, for example, its impact will be felt on inflation in many subsequent time periods. If the increase in the interest rate is maintained, then its impact will be felt over many more time periods. That is, whether the distributed lag is finite or infinite. That is a question which we will discuss later. Now, the lag is very important, as is given, as is true from this example. So, in the next class, we will explain why lags, why there is lags in the adjustment between variables.